Welcome to Medieval Tales. Before we dive into today's eye-opening story, drop a comment below and tell us, which city are you watching from and what time is it there right now? There's something fundamentally broken in the way we build homes today. In 1872, surveyors examined the Borgen Stave Church, a traditional wooden structure in Norway, during one of the harshest winters in decades. Outside, temperatures plunged to 31 degrees. Snow piled several feet deep. Winds howled through the valley with force strong enough to shred a modern expedition tent. Yet inside this church, built in 1180, with no HVAC, no fiberglass insulation, and no double-paned windows, the temperature held steady at 46 degrees. No fire was burning, no external energy source. The building itself, crafted from solid timber using methods we've largely abandoned, maintained that warmth. Now compare it to a typical modern American single-family home. If it's 14 degrees outside and you lose heat, within 6 hours the indoor temperature drops below freezing. After 12 hours, pipes burst. After 24 hours, the house becomes uninhabitable. What did builders 800 years ago understand that we've completely forgotten? In the mountainous regions of Scandinavia, hundreds of log cabins constructed between the 13th and 17th centuries still stand today. These structures have endured centuries of brutal weather, winters that would rot a modern stick-built house in weeks. They achieved this durability and efficiency with three principles almost entirely ignored by modern international building codes: massive thermal mass, absolute airtightness, and a heating strategy focused on strategic heat storage rather than constant energy burn. These three elements formed a complete, harmonious system. No gimmicks, no miracle materials, just physics applied intelligently, working with nature instead of against it. Today, we build in defiance of physics. We fight the cold with brute force energy input, and we're losing the battle. Before we dive deeper, drop a comment below. Have you ever experienced a grid failure or winter blackout? How long did your house stay warm? An hour, 6 hours, or were you seeing your breath after just 30 minutes? Share your story, because what you're about to discover will forever change how you view every modern building. Let's jump to 2010. Researchers at the Norwegian University of Science and Technology conducted a revealing experiment. They built two identical small structures, each about 430 square feet. The first was a faithful reconstruction of a 14th century medieval log cabin, solid 12-inch diameter logs, hand-hewn and joined with tongue-and-groove scribe-fit joints. No modern insulation, no vapor barriers, no pink fiberglass. The second was a modern prefabricated house built to the latest stringent energy codes, double insulation with an R value of 25, vapor barriers, triple glazed windows. On paper, the modern house far outperformed the ancient one. Both were placed in the same harsh valley. Outside temperature, 8 degrees. Both interiors heated to a comfortable 68 degrees. Then they cut the power. The modern house dropped to 36 degrees in just 9 hours. The log cabin? After 48 hours, it was still 54 degrees. After a full 72 hours, 3 days without any heat, it held at 43 degrees, well above freezing. The modern house had become a dangerous icebox, while the medieval cabin remained survivable. Why? A modern engineer might call it impossible. The log cabin's R value is only around 10 versus the modern house's 25. Higher R value should mean superior insulation, but R value measures only steady-state heat transfer. It completely ignores thermal mass, and thermal mass changes everything. A 12-inch thick wall of old-growth pine weighs about 80 pounds per linear foot. Wood has high specific heat capacity, allowing it to store vast amounts of thermal energy. When heated, the massive logs absorb warmth deep into their cores. When heating stops, they release it slowly over hours and days. The modern house? Walls are lightweight sandwiches, half-inch drywall, plastic vapor barrier, fiberglass bats, thin siding. The entire assembly weighs perhaps 10 pounds per linear foot. Zero meaningful mass to store heat. Insulation slows loss but stores nothing. As soon as the furnace stops, indoor heat bleeds out through leaks and thermal bridges with no reservoir to replenish the air. Medieval builders knew this intuitively. They harvested trees 80–100 years old, grown slowly in the frozen north. Growth rings were incredibly tight, often over 100 per inch, creating exceptionally dense wood. 1 cubic foot of old-growth pine weighs over 37 pounds. Modern plantation pine weighs just 28. That density means more mass, more storage capacity, longer thermal lag. It can take 12 to 18 hours for outdoor cold to fully penetrate a 12-inch dense log wall. Plenty of time to relight your fire. The cabin functions like a giant thermal battery, smoothing temperature extremes, but mass alone isn't enough. You need absolute airtightness. This is the second forgotten secret. Despite all our Tyvek wraps and high-tech tapes, modern homes leak terribly. Blower door tests reveal the average new home has cumulative air leaks equivalent to leaving a 20-inch window wide open. Cold air pours in constantly when it's below zero. Your furnace isn't battling the walls, it's battling an invisible open window. Medieval log cabins solved this masterfully. Logs were scribe-fitted, each one custom-shaped to perfectly match the one below, a process taking weeks or months for a single room. The result, virtually zero airflow through walls. Gaps were chinked with sphagnum moss from local bogs, material that absorbs 20 times its weight in water. Dried and compressed, it expands into every crevice. Over that, a daub of clay mixed with animal hair, usually sheep or goat, created a rock-hard airtight seal. The hair acting like rebar to prevent cracking. It's breathable, vapor escapes, but drafts cannot enter. Modern tests on 600-year-old cabins show many meet or exceed today's passive house air tightness standards. A structure built with axe and moss outperforms suburban homes wrapped in space-age composites. The third element, heating strategy. We imagine old cabins with wasteful open fireplaces, but those are thermal disasters, sucking warm indoor air up the chimney and creating negative pressure that actually cools the house. Instead, Scandinavians used masonry heaters, cakelone or soapstone stoves, weighing several tons. You burn a hot, fast fire once or twice daily. Combustion is clean and complete. Exhaust winds through internal labyrinth channels, transferring nearly all heat to the stone mass before exiting the chimney barely warm. The massive stone then radiates gentle heat for 12 to 18 hours at surface temperatures of 140–175 dig, warm enough to feel comforting, safe to touch. You can lean against it or sleep atop it. Radiant heat warms people and objects directly, creating comfort at lower air temperatures. You feel cozy at 60 degrees near a 160 deg stone wall, while forced air systems must push air to 72 degrees for similar comfort. That's enormous energy waste. A 2003 Finnish study reconstructed a traditional smokeroom cabin and tested it at 13 degrees. One 2-hour fire using about 45 pounds of wood kept the interior above 59 degrees for over 16 hours, fuel use roughly 1/10 of a comparable modern oil-heated home. All without modern insulation, just mass, tightness, and radiant heat. Interior layout, amplified efficiency. No wasteful open concept designs. Modern vaulted great rooms trap heat high while feet freeze. Medieval cabins featured low 6.5-foot ceilings and small compartmented rooms with doors, keeping warmth where people lived and worked. Bedrooms stayed cooler, fine under heavy woolen furs. This thermal zoning slashed heating demands. No need to warm unused spaces to 70 degrees. Foundations mattered too. Modern slab-on-grade concrete acts as a thermal bridge, bleeding heat into frozen ground. Scandinavian cabins rested on stone piers, elevating wood above soil and creating an insulating air gap. Thick plank floors, often double-layered with sawdust or moss between, broke thermal bridges entirely. Every detail hoarded heat. Why did we abandon these methods? Speed, cost, and cheap fossil fuels. Post-World War II, millions of homes were needed quickly. Scribe-fitting logs took months. 2x4 stick framing took weeks. Labor costs soared, but thin walls with cheap bat insulation kept material prices low. Then came the energy boom of the 1950s, 60s. Oil and gas were abundant and inexpensive. Efficiency didn't matter, just turn up the thermostat. We shifted from resilient physics-aligned building to fragile structures dependent on constant energy drip. Cut power, and they fail fast. But energy isn't cheap anymore. Grids are strained, blackouts more common, and people realize their expensive homes are vulnerable. In Europe, Germany, Austria, Switzerland are resurgence in solid wood construction. Mass timber is underway. Not nostalgia, but proven physics. Architects combine traditional principles with modern tech: thick cross-laminated timber, CLT walls, masonry heaters, compact layouts. Energy use drops dramatically, often to 1/3 of conventional builds. Power outages? Homes remain livable for days. Science confirms it. A 2018 University of Innsbruck study tracked solid wood versus conventional homes over 5 years. Wood homes used 40% less heating energy. In summer, no AC needed, thermal mass buffered heat. Residents reported fewer drafts, better humidity regulation, wood naturally absorbs and releases moisture, and healthier indoor air, no mold, no dry air issues. Durability is the final advantage. Modern homes begin degrading immediately, vapor barriers tear, fiberglass settles, studs rot behind siding. Major repairs often needed by year 30. Scandinavian log cabins? Many stand after 600 years. Initial settling actually tightens joints. A 50-year-old log home is often more efficient than new. It's an asset that improves with age. While modern builds depreciate from day one, if you're planning to build or renovate for resilience, efficiency and longevity, steal these principles. You don't need a medieval replica. Use thermal mass, consider mass timber or solid logs. If not feasible, add internal stone mass. A masonry heater or heavy fireplace surround acts as your thermal battery. Prioritize air tightness, hire professional blower door testing and seal every leak. Worth more than extra insulation layers. Design compactly, avoid cathedral ceilings, use closable rooms, embrace thermal zoning. Heat lived in spaces, let others stay cooler, think long-term. A home costing $50,000 more upfront, but saving $100,000 in utilities and maintenance over 30 years is the smarter investment. Modern codes fixate on R-value and initial cost, ignoring resilience and life cycle performance. That 14th century Scandinavian farmer wasn't primitive. He mastered applied physics. He knew heat needs mass to linger. He knew air leakage, not cold itself, is the true enemy. He knew radiant heat trumps forced air. He knew cooperating with nature beats battling it with furnaces. We traded that hard-won wisdom for speed and cheap fossil fuels. Now, with rising energy costs and wilder weather, we're paying the price. If this opened your eyes, hit like and subscribe. We're unearthing the buried knowledge the modern construction industry prefers you ignore. The medieval log cabin wasn't luck. It emerged from centuries of trial and error. Failed designs were abandoned, survivors were replicated. What endured was a robust system that carried families through 30-degree winters with zero electricity or gas. These people labored 12-hour days, built nations, raised families. They weren't fragile. They were strong because their homes sheltered them effectively, without draining resources. The secret wasn't lost. It was buried under marketing and short-term thinking. Every time you build with thermal mass, seal air leaks, and choose radiant heat, you revive that ancient wisdom. Wisdom that kept people warm in a brutal world. Wisdom that still works today. Subscribe and let's keep digging.